the club.
Great, cool. Thanks. Yeah, my name's Zoe. Title of my talk is Outer Distribution Generalization for Learning Quantum Processes. So this is joint work with Matthias, based at Technical University in Munich, Robert, who's in the audience here, and a bunch of others at LANL, or some students from LANL. Okay. Right, okay, so what do I mean by quantum process learning? Well, we're going to focus on learning unitary processes. So that's helpful, isn't it? Cool. So the idea is you probably know this already, try and find a train a parameterized unitary such that once you've got your optimum parameters, your optimized parameters, this optimized unitary is equal to some unknown target unitary. So that pink arrow points to a U. And why would we be interested in it? And so first possible use would be to better characterize an experimental system. So in this sense, it would be sort of an algorithmic version of quantum sensing. The idea is you've got some unknown quantum process taking place in your sort of closed quantum system that you want to try and learn. And effectively, you're trying to decompose it into a parameterized quantum circuit, so a gate form. So effectively, you're learning a digitalization of an analog process. And this could be useful in a whole bunch of ways, but for example, you could be trying to learn the properties of a novel optical material. You've got some novel material that introduces, I don't know, some co-nonlinearity, and you're trying to characterize what that nonlinearity is and whether there's a phase shift as well, or studying the effect of some sort of exotic laser pulse in an atomic lattice. So that was use one. Use two, in this case, maybe you actually know your target unitary, but you're trying to compile it into a more useful form. So in this case, U is known, and your parameterized quantum circuit is designed to replicate U in some more useful way. So perhaps using a limited gate set if you can't implement all gates, or with a shorter depth circuit if you, well, in all cases, shorter depth circuits are better, or a more noise dealing way, or you might want to try and compile it into a particular form for a particular purpose, such as quantum simulation, if you're familiar with our work on variational fast forwarding. And this compilation could be done either on a quantum computer or classically. So you could be classically compiling a unitary, or you could be doing quantum compilation of a unitary. And how would you go about doing that? Well, many ways you could go about doing it, but I'm going to discuss a method using quantum machine learning. So the idea is you're going to use training data to try and learn this unknown unitary. So your first goal is going to be to try and learn to replicate the effect of the unitary on a particular single input state. So you've got some state psi, you can evolve psi under your unknown quantum process, and it gives out psi out, where psi out equals U psi. And then you're going to have your guess quantum process, and you're going to fiddle around with that until you get it such that V of alpha acting on psi gives the same output to psi out. And then you're going to repeat this for a whole training ensemble. So not just one state, but you're going to have a whole set of training states. And the idea is you're going to keep on adjusting your guess quantum process, your parameterized unitary, such that you get the correct outputs on all of your training data. So your training data is just a set of states, psi I, for I equals 1 to n states in your training ensemble. And then the hope is that you're going to be able to make predictions on unseen data. So say you have some new state phi that you've not trained on. The question is, what's the effect of U on this new state phi? Well, the hope is that you can use your learnt quantum process to make a prediction. So you've got your optimized unitary V of alpha opt that you've got from your training, and then V of alpha opt acting on phi. Well, that's your predicted output for predicting the output of your process. And then the question is, well, how good are you at predicting? What type of training data, how well do you need to do your training in order to predict well? And that's what's quantified by generalization bounds. So generalization bounds quantify how well we can make predictions in terms of your training performance. So your prediction error is just going to be your difference between your true output and your guess output. So just distance between U of phi and V of alpha opt acting on phi. We choose to use the 1 norm squared because that's nicely related to the fidelity, easy to measure, but you could use other distance measures if you liked. And the quarter in front is just to ensure that our distance is between 0 and 1. Okay, so that's your prediction error on a single input, but really what we care about is the average prediction error, or the risk. So that is the average prediction error over the ensemble of states that you want to be able to predict the output of, the ensemble of states that we care about. So I'm going to denote that ensemble by P. So that average over your testing ensemble, the ensemble of states we care about predicting the action of the process over. Okay, but we don't have access to the risk. We can't actually measure it. If we actually knew what the true outputs were over all states we cared about, then we wouldn't have this problem in the first place. So what we actually have access to is the training cost. And the training cost is the average prediction error over the training data. So the ensemble of states you trained on. So now it's again an average, but it's just over your training ensemble. And I'm going to use Q here to denote the training ensemble. So the set of states, well, the ensemble of states that the training states are drawn from. So what generalization bounds do is they quantify the risk in terms of the training cost. And I'm going to draw a distinction between two different types of generalization bounds. The first one is in distribution generalization, and I have a brilliant typo here. So in distribution generalization is when your training ensemble and your testing ensemble are the same. And to the best of our knowledge, all prior results of in distribution generalization are on in distribution generalization. Now, I think that is probably a true statement. What I meant to write was, to the best of our knowledge, all prior results on quantum generalization are on in distribution generalization. And in distribution generalization is what you're typically going to use. You're going to try and train on a subset of the ensemble that you actually care about testing on. But what we decided to look at was out of distribution generalization, where the training ensemble and the testing ensemble are different. And now in general, in most contexts, you wouldn't really expect this to work. So imagine trying to train a classifier to tell apart animals and plants, and you only give it pictures of cats and cactuses, and then suddenly you throw at it a caterpillar. I mean, caterpillars are kind of spiky. Is that more like a cactus? Is a bit, I don't know, silly example, but generally out of distribution generalization is going to be a hard thing to do. But it would be good in many cases if it was possible. So we decided to investigate this. Why would it be useful? Well, in the context of unitary process learning, the test ensemble might include states that are hard to handle. So typically you're going to want to learn the process on a wide set of states, like maybe sort of uniformly sampling from the space of states. But these may require deep circuits to prepare, complex gates, and odds are they're not going to be possible to classically simulate it. So if you're trying to do classical compilation and you can't classically simulate these states, that's going to be a pain. Or if you're trying to do quantum compilation, but it requires deep circuits, that's also going to be a pain. So it would be beneficial, no matter what sort of type of quantum process learning you're doing, to be able to use a different, easier training ensemble. So our main result is that out of distribution generalization can be possible when your training data actually just involves relatively few product states. So our testing ensemble is going to be random quantum states, so states drawn according to the Haar measure, so uniformly drawn from the space of states. Now these states typically are highly entangled states, require deep circuits, complete gate set, can't be classically simulated. And then we're going to suppose that that's what you're interested in learning the action of the unitary on, but you're actually just going to try and train on a much simpler set of states, and that's random product states. So tensor product states, and these can easily be prepared, just a single layer of single qubit gates, and can also be classically simulated. And what our main result is this bound. So this is a bound on the average prediction error over random states. So that's what we have on the left-hand side in terms of the training cost, training using only product states, and this correction term. So this correction term is, again, so square root of t log t over n, where t is the number of trainable parameters in your parameterized unitary. So typically the number of angles you need to optimize, and n is the number of training states. So if you've got n equals order t log t training states, so but roughly the same number of training states as you have number of trainable parameters, that second term is going to be small. And then what it means is all you need to do is get your training cost low, just training using product states, and then you're guaranteed to have a good average prediction error over random states. So the punchline is we can learn to predict the effect of a quantum process on, well, I mean, a unitary processor on any randomly chosen state after only studying its effect on relatively easy to prepare unentangled product states. And this is going to be useful in like a wide range of learning and compiling contexts. And I presume I'm over time, so I'll just leave you with the archive link.
Questions? Yes.
Yeah, so this obviously has a lot of similarities to like quantum state or quantum process tomography, right? And the fact that, or maybe I'm wrong about that.
There are some nice ways to say it.
But the fact that just the product states are enough to get most of the process understood. Can you give some intuition about why is this working?
Okay, so I think there's two steps to the intuition. So the first is, okay, so unitaries are linear, and product of stabilizer states form an overcomplete basis. So if you had learned the effect of the unitary on all products of single qubit stabilizer states, then take a linear combination of them, act the unitary on it, you've learned it on any state. But there's, of course, an exponential number of products of single qubit stabilizer states. So that gives you an intuition as to why products of single qubit stabilizer states are enough. The surprising bit then is why you don't need an exponential number of them. Why do you only need relatively few? And to answer that, you're better off tracking to Robert, because for that second stage of the proof, we draw on their results saying that, so there's a crucial detail that I skipped over in this. The unitary, well, no, I didn't actually. The unitary need to be efficiently representable. So you need to be able to approximate it using a parameterized unitary that has a manageable number of training parameters. So if you look, if that T is large, then N is going to need to be really, really large. So for an arbitrary unitary to learn it arbitrary well, then actually there is no free lunch. You're going to need a lot of training states. But for a relatively simple unitary you can approximate, you can just do it.
Thank you.
We have one question online, but we're way behind. And
Sorry.
the question is, can we think of this as a kind of variational process tomography, which you kind of just answered?
So I think there is a distinction in the process tomography, we get a classical description, whereas process learning, where you're compiling, you end up with a sort of a quantum description because you get a circuit. That's the distinction we make there.
Okay, thank you. Hamilton, is that? Yes.